So for the final presentation of this morning, we go from the peat to clay. As presentation by Bente Lexmond. He's a PhD student within the LAS program. The floor is yours.
Thanks for the introduction, Kai. So my PhD research focuses on understanding and predicting clay shrinkage. And today I want to focus on how we measure clay shrinkage and the effect of increased pore water salinity. It's a bit different from the abstract, but I think a bit more interesting as well. So if we look at land subsidence in the Netherlands, it's on a millimeter scale, but we're so lowly elevated in many places that every millimeter counts. And here I want to highlight that in areas where there's a lot of clay present, you also see actually a lot of land subsidence. Well, a lot based on the scale. And we really want to isolate the addition of shrinkage of clays to land subsidence. So the people that have been in Flevoland, bear with me, you've seen this slide, but I just go over it real quickly again. If I'm talking about shrinkage of clays, there's two options. There is reversible shrinkage. That is if the water level lowers from an average high winter level to an average summer water level, the pores empty out and they shrink a little bit. And this is a reversible process because as soon as the water level rises, also the volume returns to its original state. It can yield up to several decimeters of land movement. So this is really important if you want to disentangle, for example, an in-source signal. And if it's differential, you get damage to buildings and infrastructure. So it's also not great for buildings. Then if we get to a more extreme situation that I've highlighted at this TS2 point, then the water level is even lower than it used to be. So it's an extreme situation. It can be due to a very hot and dry summer, for example. And what happens then is that not only these pores are sucked into each other a bit, but the soil matrix reassembles itself. So particles that have been upright, they can go into a horizontal position, meaning you lose volume, but they cannot get back up. So this is permanent, irreversible, and adds to land subsidence. And for example, in Flevoland, where we're talking about, this was up to 1.2 meters in the first 30 years. So it's an important process to take into account when, especially looking at reclaimed land. So if we describe clay shrinkage, we mostly use that, do that via a soil shrinkage curve that is shown here. As soon as it starts to dry, you lose your moisture content decreases and also your volume decreases. And the most of the shrinkage takes place in this normal shrinkage phase, in which the amount of water you lose is also the amount of volume you lose. So it's important. If your matrix gets too dense, like the shrinkage stops. And the shape of this function, the shape of this curve is a function of chemical parameters and mechanical ones, but also history. So it's difficult to make a prediction about this. But where I want to focus on today, as I mentioned, is the pore water salinity influence. So clay platelets, they have a charge deficiency actually, and they're sheet-like. So if you would look from the side, you can depict them using a line. And they have this negative charge, so they will attract positive particles in your water. And they only need a certain amount of particles to make up for this charge deficit. So if you increase the salinity, there is less water close to this clay platelet. And actually, so you lose some of the volume between the particles. And we just think that salt intrusion might yield to an increase in land subsidence, and that it continues and continues. So that's what we wanted to study. Does it affect the reversible or irreversible shrinkage and this land subsidence, this increased pore water salinity? And as we do not want to do this in a field, we do not want to salinize a complete field. We decided on a lab setup, and for that we needed minimally disturbed natural samples to be able to make predictions about the field. But we also didn't want to disturb the mechanical or hydrological behavior of the samples. And we did not find could not find a setup that was complying with these requirements. So we made one. And this is what it looks like. So to measure shrinkage, you need the volume. And we measure the volume with these optical distance sensors, which you can also see over here. So we have measure from the top and the side of the sample, and you can see. Okay, so my pointer doesn't work anymore, but you can see 3 samples. And they're on top of a high prop, which is really just a tensiometer and a black box where the sample is on. And then there's the balancers that we use to measure the soil water content. There's a few more things in the setup. So we have measurement reference tables to make sure the setup is stable. And we're using a climate controlled room to make sure we can influence the amount of evaporation. Also, we take photos. If we have some weird results, we can look back at our photos from the top, okay, to explain what had happened. And it's fully automated, so every 10 minutes we can take a measurement without too much effort. And that is what I've just shown you, that is the drying part. Before that, we need to sample. We use a specific coring set for this. The samples are about 5 centimeters high and 8 centimeters in diameter. And in this experiment, we saturated them for quite a long time with different solutions. So we have the tap water, a seawater mix, artificial, and an anion and calcium mix, which has the same negative ions as are present in seawater, and the positive ion is calcium. And after drying, we also resaturated the samples to determine what was reversible and what was irreversible shrinkage. So for the results, I want to focus on this drying part. And as soon as we started drying, as you can see over time, the volume of the samples decreased. And we have 3 groups with several samples. So you can see that samples saturated with tap water, they shrink the fastest compared to the others. But the seawater mix and tap water mix, they shrink to the same amount. Only the seawater mix is slowed, and that is because salt water evaporates more slowly than fresh water. More interesting is that those samples saturated with the calcium mix, they shrink a lot less and a lot slower compared to the other 2. And that is even more clear if we look at these soil shrinkage curves that I show here. And in all these, like in the left 2, there I want to start, you can see that this first phase that we saw in the first figure I've shown you, that was a soil shrinkage curve. There is no start of the shrinkage. There's no delay in shrinkage, so there's not many large pores in the beginning. And only the seawater mix actually shows proportional shrinkage, so the amount of water that you lose is also the amount of volume that you lose. And so we see most shrinkage in those samples saturated with seawater mix. But the most interesting one on the left with the calcium, you can actually see we wouldn't really say it is proportional shrinkage, because it's so limited. And if we look at it in the form of a table, we can see that the shrinkage is actually halved if we use a calcium mix compared to the other 2. So we have about almost 80% of the original volume is preserved if we use this calcium mix compared to the other 2, where you can see a shrinkage of more than 40%. This is quite something. And after resaturation, they all get back to the same volume, but that means still 14% is irreversible. And this clay layer was 2 meters thick, so that's more than 20 centimeters of land surface decline that you would encounter. So the real question is, what is the governing mechanism here? So the big difference between these samples is the calcium, that's why we call it the calcium mix. And there's several explanations. A lot of research has already been carried out, because calcium increases the amount of clay layers that are stacked. So there's more micro particles in your soil then. The other thing it does is that it also sticks these micro particles together to form this macro structure. And as we see directly from the beginning of the shrinkage, we see a decrease in shrinkage. It's probably these big particles that are the governing mechanism here. So to conclude with a take-home message and an outlook, we found 14% irreversible shrinkage in the clay layer. That can be a lot. It can happen in like a year time. So this could be a very fast process. But the good news is, with the right kind of solution, you can diminish the amount of reversible shrinkage and thus the amount of damage. Then we go to the outlook. So this is only the start of the work. We'll compare measurements with the lab setup, with field monitoring, and with that we can also apply the lab knowledge to the field and make predictions, and thus create a risk assessment of the risk related to clay shrinkage in the Netherlands, and hopefully predict it. So thank you.
Nice, Bente, and well in time, so that means there is plenty of time for discussions. Does anyone have a question? Pietro?
Thank you, Bente. Very, very interesting. And even though I understand that you're really at the beginning of this experimental analysis, but based on what you find, can we say that, let's say, saltwater intrusion is not really an issue, cannot cause significant land subsidence when this is the question?
Yeah, understandable. So the process we thought was super important in a soil doesn't really seem to be that important if we look at a soil. So if we only look at clay, yes, it's important. But if we look at all the other components of a soil, the importance of the process really diminishes. We see a very tiny difference in compaction over here. So it's only 3%, which is little based because, there's an error in the measurements, of course. So based on these results, no.
Yeah, thank you very much. I have one question about your irreversible shrinkage. Like after you resaturated the samples, and did you wait a time, or did you just then measure the shrinkage? Because maybe it will gain after a longer time when it's saturated, it will still swell.
It's a good question. It will swell for quite some time. We resaturate it for up to 3 months. So that's compared to 3 weeks, 4 weeks of drying.
Henk?
I'm sorry again. I'm intrigued by the 14% irreversible shrinkage. What is your assessment of that value? Is it a generic value or just the sample you had there? Because like in Flevoland, is there already a lot of irreversible shrinkage on the sample incurred in the past, and this is remaining?
Yeah, so these samples are also below the average summer level of the average summer water level. So they haven't been too ripened either. And actually, I just measured shrinkage in the samples from Flevoland, and they end up to like a similar shrinkage. So I expect actually there's bigger particles in, for example, a marine clay. So how that affects it is a bit difficult, but I think around 10% is the weird thing for something that has been saturated for at least a long time. So yeah.
Yeah, are you satisfied, Henk? Yeah.
Thank you for the presentation. Very nice. I was wondering, these numbers, 86%, are the same for every 3, and you have an average of 2 measurements, 2 to 3 measurements. Do you have an impression of the variability? Really every sample, every measurement is 86%, or is there some variability between them?
There is some variability in there, yeah, for sure. Mostly, we started over 3 samples for each group, but I got COVID, so I wasn't able, there's a few of these things that happened, so we ended up with only 2 or 3, only 2 measurements. Mostly, in most groups, they were very similar. Like you can actually see also in the curves I've shown you, yeah. And also we analyzed them afterwards, so if there is something up with the sample, mostly it's because there is a piece of wood or reed or something also in the samples. So that explains a lot of the differences.
Yeah, Philip.
Yes, thanks a lot, Bente, for this great talk. Have you also dried again the re-wetted sample? And what would happen? Would we get again this 14%, or would it be actually zero if you then re-wet it again? So is it a one-time irreversible process, or?
Yeah, we started redrying them. A few, not all of them, but a few. The measurement setup broke down, unfortunately, but we still see some shrinkage. The part that we've measured, there was still shrinkage. Yeah.
So that's the clear
cannot be
fact.
conclusive yet. Sorry.
Thanks.
I really want to ask a small question. Do you think it matters whether the clay particles were deposited in a saline environment to begin with? I mean,
Yeah.
there's of course a gradient also in the Flevoland, and vertically and horizontally. And I think these were all deposited in quite, let's say, in the tidal environment, right? You didn't go deeper to the more lagoonal clays.
So these are all fluvial samples.
Oh, these are all fluvial.
These are
Sorry, I missed
fluvial,
that.
yeah.
Sorry. Yeah.
So yeah, because otherwise in a marine environment they're deposited with salt, and that creates bigger clay particles.
Mm-hmm.
So we expect less shrinkage in those.
Yeah, very interesting. So I think this is about it, right? Yeah.
Yeah,
Well,
enjoy lunch.
Yeah. Well, let's give you applause, of course.